Hello, welcome to Lab1, Constant Velocity, created by me, Andrea. To get us started, I want to identify our system and our surroundings. So our system is going to be a marker, and then our surroundings are going to quite literally be everything else. Now, the purpose of this lab was to observe the position of an object moving with a constant velocity, meaning that the object was moving with the same speed without changing direction over some time interval, and then compared the observed position to the predicted position, which was calculated using a computational model. So, how do we do this? Using Tracker to document the object's position as it is moving, we can record data points, position, and time. Using these data points, we can then calculate change in time, change in position, and velocity. We can then take these calculated values and plug them into our GlowScript code to create a computational model. We can then create a graph using the Tracker dataset and GlowScript dataset and compare the two graphs. Now here, it's important to tell you that the graph created by Tracker is going to be our observed position graph, and the graph created by GlowScript is going to be our predicted position graph. Here we are plotting on a position versus time graph, where the x-axis is time and the y-axis is position. Now this lab resulted in two different lines. A linear graph, this graph corresponds to the one produced by GlowScript, and an almost linear graph, and this graph corresponds to the one produced by Tracker. While there was slight deviation between the two graphs, both graphs effectively show my object moving at a constant rate. Now, the reason for the slight deviation in the graphs is because there are some outside forces acting on the marker. Therefore, the observed position graph does start to dip towards the end. Now, one equation to keep in mind is Newton's second law, or the momentum principle, which states that at any instant of time, the net force on a body is equal to the body's acceleration multiplied by its mass, or equivalently, the rate at which the body's momentum is changing with time. So if we start with the equation F net is equal to the change in momentum over the change in time, we can derive it to get what we call our velocity update formula, which I'm going to show you now. As you can see, we end up with what we call the velocity update formula. And what this formula is telling us is that if the total force acting on the system is equal to 0, then our velocity is going to be constant. Now here I have inserted a video of me using GlowScript, which we use to create our observed position graph. To the right, you can see data points time, x, and y. Here, y data point is not important. We place the data point at the center of mass of the object, which I decided to be the end of the marker, and then tracked it with certain time intervals. Now, our tracker analysis. The total time we recorded was 0.667 seconds, and our initial position, which can be seen above, is equal to 0.0129 meters only in the x direction. And our initial velocity, which can be calculated by placing the change in position over the change in time, which gives us 0.4421 meters per second only in the x direction. We do not have velocity in the y direction. We can then take these data points and insert them into our computational model. Here we set the net force equal to 0 because, as we saw in the velocity update formula, if we want a constant velocity, the net force has to be equal to 0. We then input our initial velocity as well as our initial position. We also change delta t to be our time intervals, 0.033 seconds. The mass of the ball does not affect the ball's velocity, since according to the update formula, it will just equal 0 if the total force is equal to 0. And then we also insert our ball position, or our position formula, which we'll use to create the graph. Now, here's the graph produced by our predicted position, as well as our observed position. As you can see here, the predicted position is linear, but our observed position starts to dip towards the end. Now, what could be the reason for the differences in the two graphs? Outside forces. There are outside forces acting on the marker, such as force of friction and air resistance. As well, we can also have a problem due to rounding error, which can cause slight deviation in the results, as well as position tracking. I may not have placed the center of mass of the object at the same spot every single time, which can cause a few deviations. Now, let's look at a few questions. What if the positive x and negative x were interchanged? Well, really, we wouldn't see anything besides a negative slope. So not much change. The slope is just negative now, as you can see here. Now, is the net force equal to 0? In the x direction, no. The computational model overestimated the position of the ball at the designated time intervals towards the end. Therefore, we can conclude that there are other forces acting on the marker. Friction or air resistance, things such as that. And in the y direction, the net force is equal to 0 because our object is not moving up or down. That's all. Thank you.